Welcome to Ask and Learn.
In this problem, we are given a beam with two discrete downward-facing force vectors on the top, one at 0.3 meters from far right, one an unknown distance from far left. And on the underside of the beam, we're given a linearly varying force density that spans the entire length of the beam. We have givens of, for this force density relation, an initial y coordinate, W sub A, of 20 kilonewtons per meter, and the entire span of the beam is 1.8 meters. The magnitudes of the two downward facing force vectors are 24 kilonewtons and 30 kilonewtons. In this problem, given this linearly distributed upward force, we're asked to find the distance A, that's the distance from far left to the location of the left downward force vector. Find that distance A and the corresponding value for W sub B, which is the y-coordinate of the final point of our linearly varying force density. Find those such that the system is in equilibrium. And as already said, we're given this time, as opposed to the previous problem, W sub A equals 20 kilonewtons per meter. We will first find the total load and centroid from the two downward force vectors. Then we will write out a linear function of the force density relation. All right, and that's a of the upward facing reaction force. We will evaluate integrals to find the total load, F sub tot, and centroid, X sub tot. We will write those in terms of the two parameters we're trying to solve for, A and B, and then we'll solve for them using those two equations. We'll solve for those two unknowns. Step one, finding the total force load. We have 24 kilonewtons plus 30 kilonewtons equals 54 kilonewtons. To find the centroid, we're missing a piece of information to get a numerical answer, so we'll have to leave it symbolic. But basically, that's the moment arm measuring from far left of the left force vector of 24 kilonewtons plus the moment arm from far left of the rightward force vector, and it's 1.5 newtons from far left. It has a magnitude of 30 kilonewtons, and we're going to divide that by the total load. Since we don't know what A is, that's something we'll have to solve for. We have to leave the equation in this form. Step two was to write out the equation describing the linear force density that points upward. We find the slope, which is the final y-coordinate, W sub B, minus the initial y-coordinate, W sub A, equals 20 kilonewtons per minute. And that difference we divide by the total span of the beam of 1.8. Here, this is our slope term. For a linear function, we multiply the slope by the independent variable, the location along the beam, x, plus our offset. And here we're given an offset of 20 kilonewtons per meter. And it goes to, we should note that our coordinate system is such that x goes this direction and our y coordinate goes this direction. Step three, we're going to write out and evaluate the total load of the force density. And for an equilibrium, I'm skipping ahead a little bit, but for it to be an equilibrium, this must exactly cancel the total load of the two downward forces. And we're also going to write out the centroid times the total load, which is equal to this integral on the right-hand side. It's the product of the beam coordinate x times the linear force density times the infinitesimal dx that integrated over the span of the beam from 0 to 1.8. We first evaluate the total reaction force, that which exactly counters the total load, evaluating our linear function that we derived here. The x term goes to x squared over 2. The constant term goes to 20x. And we're going to evaluate from 1.8 to 0. And since it exactly opposes the total load, we can put that here as 54. We're not going to worry about signs here. We're going to leave these as magnitudes. So after some simplification, we are left with WB minus 20, that difference times 0.9 plus 1.8 times 20, that 1.8 came from the span of the beam, equals 54. We can solve for WB, and that comes out to 40 kilonewtons per meter. That's actually the answer to part B of this problem, just to keep things straight. Next, now, given that we now know the value of W sub B, we can calculate a numerical value for our centroid. Doing the integral of our centroid equation here, this time we have the product of x times our linear force density times dx evaluated over the span of the beam. The x squared term, the integral of x squared is x cubed over 3. The integral of 20x is 20x squared over 2. We evaluate from 0 to 1.8. Those numbers condense down to 1 meter. 1 meter is the value of our centroid. So that's a valuable piece of information, but that's not what we're asked to solve for. We're asked to solve for, basically, given that centroid, where is the location of the left downward force vector? And that location, that span, we're calling A. So we can go back to our expression we did up here in step 1 that contains A and set it equal to 1 meter, our numerical value for the centroid of the upward force density. Doing that, we have 1.0 meters, it should be here. In the numerator, the product of 24A plus 45, that sum divided by 54 gives us 24A equals 9, and we can solve for A, which is 3/8 or 0.375. And that is the answer to part A of this problem.